Hi! In this short lecture I want to present my personal choice of some interesting astronomical results obtained in 2022. Definitely in the history we'll remember this year in astronomy as the year when the James Webb Space Telescope started to produce its first results. There are many lectures, papers, presentations about these results, so I will not repeat them in detail. I just want to start with mentioning that in 2022 the most interesting results were related to galaxies and to exoplanet studies. The first publication was published in July. This set of results I'm presenting is mostly based on publications in the archive, on the website archive.org, and in the left bottom corner you can see the number of the paper, 2207, that's the year and the month, and then the number of the paper in a given month. So this paper was published in the end of July, and it represents the results of the early release of scientific data from the James Webb Space Telescope. And as I said, mainly these results are related to studies of galaxies, including those which we see in the youth of our universe, and exoplanets. Also, there are several beautiful images of different types of nebula, and indeed observations in this part of the infrared are extremely interesting in this context. But again, I'm not going in details here, but I want to describe one result obtained using the James Webb data this year. So this is a result about atmosphere of an exoplanet. This is a well-known exoplanet, WASP 39b, and this result is remarkable despite there are no beautiful pictures. It's not about early universe or something like that. This is detection of SO2. The observers found definite signs of the presence of this substance in the atmosphere of that planet. And this is important because we want to understand properties of atmospheres of exoplanets really in details. And in the scheme in the middle you see how this molecule can be produced. And these blue-green arrows, they represent the main formation channel of SO2, and this is the channel which is related to photochemical reactions. So this discovery is the first discovery of a molecule which is produced by photochemical processes in an atmosphere of an exoplanet. In my opinion, studies of exoplanet atmospheres are very important, not just by themselves, not because we're interested in exoplanets. There is something more important. If you consider what is the most important scientific problem of the present day, maybe these are several problems related to evolution of the global climate on Earth. We do not understand it precisely on the time scale starting from several decades, and we are really very interested in it. And this is a question which costs a lot. And to produce good models for the Earth climate, we need much deeper understanding of different physical processes in the atmosphere of our planet. And typically, to develop a very detailed model with many ingredients, you need to study different parts, different sections of this model using different sets of observational data. And having just the atmosphere of the Earth and several other planets in the solar system, actually you cannot probe all possibilities. But step by step we start to study in more and more detail atmospheres of other planets. And now we have James Webb in the orbit, and it's quite important to learn more about physical processes in atmospheres of exoplanets. Very soon a new European satellite, AREL, will be launched, and this satellite is specifically dedicated to studies of exoplanet atmospheres. And in my opinion, all these studies will push significantly the whole area of atmospheric physics, and these will bring more talented young researchers to the field. This will produce lots of different codes which model evolution of atmospheres, their properties, and so on. So that's why I decided to choose this particular result from the James Webb Telescope to discuss it in some detail. Okay, that's enough for the James Webb. It's a wonderful instrument, but it's not the only high level instrument in orbit now. And maybe for the whole astronomical community, the most important instrument in orbit is the European satellite Gaia. In 2022, the third data release was released. Gaia is observing since 2013, and it already fulfilled its core program. But luckily the satellite is functioning perfectly, and till it's possible, observations will continue. So they will continue for a few years more, and this satellite produces huge set of data which finally will be all in open access. But initially it's necessary to do some data reduction, which can be done only by the team specifically focused on this topic. So there'll be several data releases, and now we have the third data release. All subsequent releases, they contain more information. This doesn't mean that there'll be more and more sources in the data set, but for more and more sources there'll be more and more detailed parameters. In the third data release, now we have much more spectral data, and also all subsequent releases include longer periods of observations. In the third data release, we have now the first 34 months of observations, so nearly 3 years. And definitely different teams or even individual astronomers all over the world, they get ready for the new data release. They work with the data from previous releases, and immediately when the data is in the open access, people put their hands on it and start to run their codes, and so new results appear very rapidly after the publication of the data. So it's not a miracle that in 2022 many new papers appeared which use already data from data release 2. Okay, so let me describe 4 results published this year. 3 of them use DR3, and 1 actually uses early release of DR3, so not the complete set. Well, so the first result is related to white dwarf studies. White dwarfs are products of the stellar evolution. Stars like our Sun end their lives as white dwarfs. So these objects are quite numerous. They have quite interesting physics, which is not completely understood. But what is more important, maybe, the history of the galaxy is written in white dwarfs. So if you study these types of objects, you can follow evolution of the star formation in the galaxy even with some spatial resolution. You can follow chemical evolution of the galaxy. So these bodies are quite important. To do many advanced studies, you need you do not need just lots of sources. You need a complete sample. And in this paper, published in November, as you see, the authors present the complete sample of white dwarfs inside 100 parsec around the Sun. This is a huge result, really. So it contains nearly 13,000 white dwarfs. And the whole set of white dwarfs in the DR3 is, by the way, about 100,000. So the authors analyze this sample inside 100 parsec. They represent lots of statistical data, and definitely this result is very welcomed by many researchers working on white dwarfs or on the evolution of our galaxy and so on. So in my opinion, this is quite an important result, which will be highly cited, by the way, in near future. The second result I want to mention is also about compact objects, but now about neutron stars and black holes. When in 60s, before discovery of radio pulsars, before discovery of black hole binaries, people already discussed how it's possible to identify these sources. And Zeldovich and Guseynov in 1966, if I'm not mistaken, put forward a nice idea. You can use a very simple approach, actually used before for different types of objects in normal stellar astronomy. You study binaries. Neutron stars and black holes are products of stellar evolution. Many stars are born in binary systems, or even in triple, quadruple, and so on. And so some of neutron stars and black holes remain in binaries after their progenitors end their lives. So you can imagine that you don't see a neutron star or a black hole because there is no accretion and they're not bright sources. But looking at the normal stellar companion in a binary, you can notice that this normal star is a member of a binary system. How you can do it? There are two ways. The first, you can take spectra, and you can identify in spectra of selected binaries that lines are periodically moving because of the Doppler effect. This means that the star is orbiting around the center of mass of the system. So you can determine the orbital period. You know the mass of the visible star, so you can calculate the mass of the invisible companion. If it is dark and massive enough, you can conclude that this is a neutron star or even a black hole. The second approach is even more simple, but actually more difficult technically. When a star, a normal star, a visible star, is moving around the center of mass, you really see that it is moving. So it draws a small ellipse on the sky when it moves around the center of mass, and you can notice it. However, of course, the shift in the position of the star is really tiny. It's very difficult to measure it. So step by step, with new instruments, people now start to look for neutron stars and black holes in binary systems without accretion, without any type of activity of a neutron star, I mean radio pulsar, magnetar activity, and so on. And they use both approaches. Thanks to many spectral measurements for stars done with the James Webb Telescope in China, there are several candidates due to radial velocity variations. However, in this paper, the authors use another approach. So they use astrometry from Gaia, and they really look for periodic changes in the position of the star. So they start with the binary catalog in the third release of Gaia, and this catalog includes about 135,000 binaries. So working with this huge set of data, they are finally presenting a sample of just 24 systems, but these systems are really good candidates to host a neutron star or a black hole. They have orbital periods about a year, which simply depends on the data set. So we see only one star in a binary, so the second companion is not visible, it's a dark companion, and you have to select a mass limit to deal just with neutron stars and black holes, and the most natural choice is the Chandrasekhar mass, 1.4 solar masses. Actually, neutron stars can be less massive, and it's well known from radio pulsar measurements, binary radio pulsar measurements, that neutron stars definitely can have masses down to 1.18 solar masses. Maybe they can be slightly lighter. So there is overlap in the mass distribution of white dwarfs and neutron stars. And also it's important to underline that massive white dwarfs are actually quite rare. So larger is the mass of the white dwarf, less is the number of such objects in the galaxy. So 1.4 is a good choice. And of course, you never measure the mass precisely. You measure some distributions. You have some probability that the object has such and such mass. So this 1.4 is not a very strict limit, as you see in the plot. On the horizontal axis, this is just the number of the system. And on the vertical axis, that's the mass of the invisible companion. And you see that for each system, you have some distribution, this 50 grades of gray. And some of them go down below 1.4 solar masses, but that's fine. Still, there is a high probability that this object is a neutron star. You cannot prove it definitely at the moment, at least, but there is very high probability that that's a neutron star and not a white dwarf. Visible companions in these systems are mainly solar type stars, so FGK dwarfs. There is one hot subdwarf also. And there are several important results visible here. One of the most important probably is that there is no gap in mass distribution between neutron stars and black holes. When we measure masses of neutron stars and black holes in X-ray binaries, and for neutron stars also in systems with radio pulsars, we actually see a gap in the mass distribution. Neutron stars cannot be more massive than roughly 2.2 solar masses. We do not know exactly this limit. It might be, by the way, very sharp. So it's somewhere around 2.2 solar masses. But black holes in X-ray binary systems typically do not start at 2.5, for example, solar masses. Mostly we see black holes starting with 3 or even 5 solar masses. So in between there is a gap. Step by step it's filled by different approaches. We can use gravitational wave data to probe this range of masses. And as you know, probably in LIGO, in their classification, so separately they have neutron stars, black holes, and systems from the gap. That's one piece of information. Then also gravitational microlensing can provide some statistics to probe mass distributions of compact objects, and now there are about a dozen of good candidates for isolated neutron stars and black holes detected by this method. Hopefully soon, especially using the Nancy Grace Roman Space Telescope, known before as WFIRST, we'll see lots of isolated neutron stars and black holes. Also Gaia can contribute here due to astrometric microlensing. But up to now, a sample of 24 sources which are not radio pulsars or X-ray binaries, it's quite a significant sample, and it's very interesting that there is no gap here. It can be very important for models of core collapse stars, of massive stars, because of course they are main progenitors of neutron stars and black holes. Okay, let's move on. The next result is about exoplanets. Actually, it's expected that in maybe tier 5, so in a few years, Gaia will start to produce a huge number of exoplanet discoveries. But this will be done due to astrometric detections. This is a new method, I would say. I mean, the method is known for ages, but up to now there is just one strong candidate to be an exoplanet discovered by astrometry, and what is surprising maybe, it's due to radio observations. So people observed a red dwarf. Red dwarfs are known radio sources because their activity, and they found that the dwarf is a member of a system, and determination of the mass of the invisible companion gives us the result below 12 masses of Jupiter, so most probably that's a planet. Actually, it's more like a Saturn. But that's the only result, and we're still waiting for astrometric detection of exoplanets by Gaia. Still this year, Gaia started to fill the list of exoplanets, and we have Gaia 1b and Gaia 2b, two exoplanets, two hot Jupiters, discovered by normal transit technique. Gaia collects a huge set of photometric data for more than 1.5 billion stars, and of course this data can be reduced to look for transits. And what is important in this paper, it's not that people discovered another two hot Jupiters. There are lots of known hot Jupiters already, and nothing specific about these two. What is important is that they developed a method, an algorithm, which can successfully detect transit planets in the Gaia data. This result was validated using data from the TESS satellite, and also it was validated by dedicated spectroscopic observations with a large binocular telescope. So these detections are very solid. And so now people have a good method, probe method, tested method in their hands, and with new releases which will cover longer periods of observations, they might successfully detect lots of transiting planets. So we're waiting for new results when this data is public. And finally, another result from Gaia. This I choose it mainly for fun. It's quite an interesting result. Maybe not too much big science, new physics or something like that inside, but it's just beautiful. We know that now Proxima Centauri is the closest star to the Sun. But of course it was not so before, and it will change quite soon on astronomical time scale, because stars are moving relative to each other. It's known that relative velocities of stars in the solar proximity is about 10 kilometers per second. Sometimes it's difficult to judge how significant it is. Now let's put a different question. How long shall we wait that two stars, two randomly chosen stars in the solar vicinity, move from each other or towards each other by 1 parsec? 1 parsec is a typical separation between stars. And this time period is not too long, it's like 100,000 years. In the third data release, now people have lots of data about stellar velocities. And so the author of this paper, published in July, made a study looking for stars which passed near the Sun during last 10 million years, or for stars which will pass close to the Sun, I mean within 1 parsec, in the next roughly 10 million years. And you see the results on the plot. Color represents the relative velocity of the star and the Sun, And squares correspond to questionable candidates, so that is not that precise, and circles to good candidates. And we see that two closest passages of stars near the Sun are quite solid results. So we have circles, and these are very low velocity stars. So one passage close to the Sun happened slightly less than 3 million years ago, and the distance was 0.05 parsec, and the next close passage will happen in roughly 1.3 mega years from now, and the distance will be comparable, about 0.06 parsec from the Sun. That's quite interesting because such stars might interact very actively with comets in the Oort cloud. So it even can have some effect on the Earth. And I don't know, if you are writing science fiction, you can use this new result to use some real data in your novel or in your story. Okay, enough for Gaia, and then I'll present several separate results and, well, not very different subjects. These are individual results obtained with quite different instruments and technique. And again, I start with close passages, but now it's not the Sun and the star, but a supermassive black hole and the star. So it's well known that there are stars around our supermassive black hole, Sagittarius A star, and thanks to such observations of these stars, we know precisely the mass of the supermassive black hole, and people continue to follow orbits of these stars, and they look for new stars, and continuously they find stars with shorter and shorter orbits, so with smaller and smaller semi-major axes. And now we have a new record. The star is called S4716. It's quite difficult to observe the central region of our galaxy due to interstellar absorption. And so people use infrared observations, but with large ground-based telescopes. Typically, it's VLT in the European South Observatory. You know that there are 4 8-meter telescopes there. They can work together in the interferometric mode. And also Keck telescopes are used. So this new star has an orbital period about 4 years, and the semi-major axis is about 400 astronomical units. The orbit is eccentric. So in the periapse, the star comes down to 100 astronomical units from the central supermassive black hole. This is quite interesting because with such stars you can get data more rapidly. Detailed observations of these stars are used to probe theories of gravity. So that's quite an interesting additional method to look for new physics. And of course, when you find stars closer and closer to black holes, the effect is stronger and you obtain the data more rapidly. Also, there is an interesting question how stars come to these orbits, and this question, by the way, is not answered completely. Most probably stars participate in several body, 3-body at least, interactions in this S cluster around the black hole, and so they change their orbits. Their orbits are modified due to this interaction, and so they can be settled on very short, very compact orbits, very often very eccentric orbits about the central black hole. Okay, this is another record related to neutron stars. A radio pulsar with the longest spin period, 76 seconds. That's a huge step forward because the previous record was 23 seconds, if I'm not mistaken. This pulsar was discovered by Meerkat. That's a set of radio telescopes in South Africa. And also for this pulsar, the period derivative was measured. If you have a period and period derivative, using the magnetic dipole formula, you can obtain an estimate of the magnetic field. And for this radio pulsar, it's quite large, larger than 10 to 14 Gauss. Let's have a look. We see these dashed inclined diagonal lines. They correspond to constant field, estimated with the magnetic dipole formula. So 10 to 15, 10 to 14, 10 to 13, 10 to 12, which is called the typical magnetic field of radio pulsar. So you see this line passes through this crowd of dots. Each dot is a radio pulsar with measured period and period derivative, which is on the vertical axis. Why this object is interesting? Because we do not know how it was formed. There are two main options. Normally, radio pulsars evolve from left to right following a line which is parallel to one of these dashed lines. This means that evolution proceeds with a constant magnetic field. This is fine for radio pulsars. However, together with Andrei Goshev a few years ago, we showed that maybe there is a brief period of time when magnetic fields of normal radio pulsars also decay by a factor of 2, but this doesn't change drastically the magnetic field. The situation with magnetars, they are shown with these magenta squares, is quite different. Magnetars are visible, they shine because of the energy of their magnetic field. So they dissipate this energy and magnetic field is decaying. So for magnetars, evolution is not parallel to these lines, it goes down. And such models help to explain why there are no magnetars with spin periods much larger than 10 seconds. So all evolutionary tracks just goes down here. And then they can stop rapid field dissipation and proceed more or less parallel to one of these dashed lines. Okay, but what about this guy? It's quite improbable that it evolved just from this region of magnetars, because its magnetic field doesn't look to be dissipated, and it's strange. Or maybe it started already with a long period, and now there are models to explain it. Models, at least they were modified specifically to explain this object. They include so-called fallback accretion. After a supernova explosion, significant mass fall back to a neutron star. So this mass is gravitationally captured. And interaction of a neutron star with this mass, which can form a disk around the neutron star, can result in significant spin down, in slowing rotation of a neutron star. So maybe this new pulsar does not have a real age of 5.3 mega years. Maybe it's much younger, but it was born already with a long period. Then potentially it can be even a magnetar. We didn't see any traces of magnetar activity from this source, but maybe we have just to wait, and that's quite interesting. Also, I can mention another source widely discussed this year. It's on the top, this gleam blah blah blah, represented by this red arrow, and it has spin period about 18 minutes, quite a lot. The period derivative is not measured, there is only an upper limit. So this point where this arrow starts is the upper limit for the period derivative. So actually we don't know the magnetic field of this object. Even more, we don't know if this is a neutron star or not. Potentially it can be also a white dwarf. In this plot there is one white dwarf, this AR Scorpii. This is a white dwarf showing radio pulsar-like activity, and this source gleam is quite intriguing in this respect. Okay, let's move on and let's look maybe at another record related to neutron stars. A very massive neutron star, another new pulsar. This is a millisecond pulsar in a binary, and this is a pulsar in the galactic disk. Many millisecond pulsars in binaries are found in globular clusters, but this guy is in the galactic disk, And for millisecond pulsars in the galactic disk, that's the most rapid rotation, 1.4 milliseconds. That's important. Pulsars cannot rotate more rapidly than 1 millisecond, roughly. The exact limit depends on many things, and some of them are unknown, but 1 millisecond is typically the limit. Okay, this pulsar is a member of a binary, and the pulsar is belongs to the class Black Widow. So you see that Black Widow is a pulsar with a low mass substellar companion, and previously there was accretion from that companion on the neutron star. So the neutron star was spun up by accretion. That's why a millisecond radio pulsar was born. So these pulsars are recycled. And now the pulsar is irradiating the companion, and so it's evaporating the companion. That's why they're called Black Widow. Okay. Many of you know that precise measurements of masses of neutron stars are possible in binary systems with radio pulsars, but when we observe different post-Newtonian effects, when we can see up to 5 effects of general relativity, and then we can determine the mass with better than 1% precision in some cases. In the case of Black Widows, another approach is used. People used optical spectral observations of the visible substellar companion. And this is quite different. There are some issues with these approaches. So precision is not as good as for many binary radio pulsars. Still, now it seems that main problems are solved, so these mass determination are quite robust. And for this new pulsar, the central value, again, I remind you that you never measure a precise value, you measure some distribution. So for this new pulsar, shown with blue, the maximum corresponds to the mass 2.35 solar masses. Uncertainties are quite significant, so it well can be how many 20% of the probability that the mass is below roughly 2.17. That's a very important limit. I on purpose showed it with this thin red line, this vertical line. But still it can be more massive. That's more probable, and this is very important. What's specific about this 2.17? This is the value of the maximum mass favored by gravitational wave data. Up to now we have just one very good example of neutron star coalescence, which produced gravitational wave signal plus a gamma ray burst plus a kilonova was observed later on. And detailed analysis of this source together with some other data points towards the maximum mass about 2.17. So people like very much that value. Probably here we have a problem. Probably we have a neutron star which is more massive, so that's quite interesting. So we have to wait for new detections of coalescence of two neutron stars and to maybe new observations of this pulsar, which might help to make the uncertainty smaller. As many of you can know, I'm very interested in fast radio bursts, and it would be strange if I do not include any results about these sources in my short review. So I choose just one result on, say, normal fast radio bursts. It's quite intriguing. Early this year, the preprint appeared in February. People presented a very intriguing result. Observations were done with the Hypertief system in Netherlands. This is a burst with a complicated structure, so that's one burst. Duration is, you see, a few milliseconds. Look at the horizontal axis. This is a non-repeating source, so no other bursts from this source were ever detected. And there are 5 distinguishable components in the burst. And people analyzed the separation between these components. Even by eye, you see that it looks they have the same separation. And indeed, at significant but not very large probability, so the result is less than 3 sigma, it's about 2.5 sigmas, there is a periodicity, and periodicity is 0.4 millisecond. So this cannot be a spin period of a neutron star, because neutron stars, unless this is a bar quark star, cannot rotate that rapidly. So this might be something else, and that's very interesting, because it can have something to do maybe with the emission mechanism of fast radio bursts. The emission mechanism of fast radio bursts is not known yet. Even there are two families of models. Those who are interested, you can find my short review published in the archive in October. And these two families are magnetospheric. This means that the radio emission is produced in the magnetosphere of a neutron star, of a magnetar most probably, because magnetar models are now more favorable. Or radio emission is generated in a relativistic shock at significant distance from a neutron star. This distance is about 10 to 14 centimeters, quite a lot. And this fine structure of the pulse with a high probability of periodic structure can be a good, not final, but very good argument in favor of magnetospheric models. Of course, you can form a similar structure also using a relativistic shock, but it's less trivial. And it's more natural to say that step by step magnetospheric model starts to win. However, it's not for sure yet, and this field of research is quite interesting now, and people are spending lots of time, investing lots of time to make new models of emission of fast radio bursts, to obtain new observations and to confront models against these observations. Before I was focused only on papers from the archive, but at the end I want to show two results which are not published in the archive yet. Both of them are from October, so they're quite recent. As you know, fast radio bursts were discovered in 2007, and already in 2007 we, together with Pasnov, proposed that magnetars are sources of these events, extragalactic magnetars, because it was sure that sources are extragalactic. However, for years there was a nasty question: why don't we see any fast radio bursts from galactic magnetars? There are about 30 galactic magnetars known, and for years they showed nothing like fast radio bursts. But in April 2020, so 2.5 years ago, finally people detected the first short radio burst from a known galactic magnetar, which was accompanied by a normal, more or less normal, high energy burst. At that time the radio burst was detected by CHIME in Canada and by STER-2 in States, and by 4 different satellites, by the Chinese satellite InSight arhe.msk, by the Italian satellite Agile, by the European satellite Integral, and by detectors, Russian detectors Konus on board of the American satellite Wind. Since that time there were no such events from that magnetar. I mean, there were lots of radio bursts detected from this magnetar, there were lots of X-ray bursts detected from this magnetar, but they never came together. And in October this year the situation changed. Now we have 2 more examples. They are published yet only in Astronomer's Telegram, and numbers are below for those who are interested. I'm sorry that there might be also 2 other numbers, 15707 and 15708. These 4 numbers is for the first burst on October 14, but for the second burst there are 2 more telegrams. Again, 15707 and 15708. Well, so now we have 3 examples. That's quite interesting. What is also interesting, however, it's just a preliminary. The first burst detected in 2020 was in X-ray somehow peculiar. It was not very typical for that source, but it seems that bursts detected this October, they are more typical. It is also very interesting for the mechanism of fast radio burst emission, and we're waiting for complete papers. Maybe people are submitting their papers to Nature or Science, so it takes quite a long time when these submitted papers pass all steps before they appear in the archive. Another interesting result which was obtained this year is related to gamma ray bursts. In October again, a very strong gamma ray burst was detected. However, it's quite a distant event at the redshift 0.15, which correspond roughly to 2 billion light years from us. So by itself the burst is interesting, it's very powerful, but not just it's energetic what attracted lots of interest. 2 telegrams, one in GCN and another in Astronomer's Telegram, appeared from 2 different detectors, LHASO and Carpet-2. Both of these detectors detected very high energy photons from this burst. LHASO detected 18 TeV photon. That's all right. This is interesting, but this can be explained in standard physics. But the result from Carpet-2, that's a Russian device, is more interesting. They detected a photon with a huge energy, 250 TeV. This is a problem, because gamma ray with such huge energy simply cannot propagate for 2 billion light years in the intergalactic medium. It might interact with other photons, and so you have to invent something new. So you need new physics to explain this result. And that's why many theoretical papers with different approaches appeared during these 2 months. And one of the possibility is that the source is emitting not only electromagnetic waves, but also axions, hypothetical particles, which are much welcomed by theorists. And this axion propagate for some distance, and then is converted into a high energy gamma ray photon. And then we detect this photon, but the photon didn't made all the way from the source towards the observer. That's quite an interesting possibility, but it's necessary to wait for a complete paper about this result, about this detection by Carpet-2, because if the energy of this event is slightly less, then actually the problem is not so strong and it can be explained in the conventional physics. So that's again a very intriguing situation. Well, that's all what I wanted to say about the previous year. Now what we can expect from the next year. Of course, the most interesting discoveries are serendipitous. But still we can make some predictions because we know which huge instruments will start working next year. And I selected 2 examples. The first is the LSST telescope. This is a huge machine which will start working next year, and that's the first really large, that's an 8-meter telescope with very large field of view. So it's not pointing to particular sources, it's scanning the sky, and that's a big data project. So people for years developed new algorithms to deal with this data, And there are many groups all over the world which will work with this data, looking for new transits. People can study solar system objects, extragalactic objects, everything. They can look for optical counterparts for fast radio bursts. So many new tasks can be done with this telescope. Many new, for example, interstellar comets and asteroids can be detected. Maybe, well, I'll say quite probably that it will find new types of optical transients, so we expect many results. As I said, the instrument might start working in 2023, so maybe first really important scientific results will appear only in 2024, but it's also not so long to wait. What else will happen next year? Gravitational wave detectors will start their fourth scientific run next year, and now we'll have 4 detectors: 2 LIGOs, Virgo and Kagra in Japan. Kagra, sorry, in Japan. And what's important, that all 4 detectors were significantly upgraded. So they have larger sensitivity, which means more sources to be detected. And it's not just to increase the number. We cannot look specifically for interesting events. For, I don't know, new neutron star coalescence with electromagnetic counterparts, coalescence of very massive black holes, or black holes with huge mass ratio, or something else interesting. We have just to look for more and more sources, and more sources we detect, higher is the probability that we detect something really interesting. And so we can expect that the 4th run will be very productive. It might be quite long, so hopefully. The 3rd run was terminated a little bit earlier than it was planned because of the pandemic. And hopefully the 4th run will be okay. And we can expect you have new interesting discoveries from gravitational wave detectors. Okay, that's all. So I'll stop here and hope to bring you new interesting results in a year. Bye.